want you to be super warm and super supportive and super welcoming. Thank you so much.
Just give me a second.
Okay. Hello. My name is Kentaro Matsumae. I'm an iOS engineer working at Mercari. Today, I'm going to talk about super resolution with CoreML. Mercari is a developer of marketplace app. The company has offices in Tokyo and the US and the UK. And each team develops app for each region. I work in the Tokyo office and developing a payment system for this app. However, today's talk is based on things I learned during my last job working as a manga app developer. Until 6 months ago, I was developing a manga app. Manga is another word for Japanese comics. Manga app's main contents consist of image data such as this. This app's main purpose is to gather a large number of these images, from the server and display them. Because of this, improving data transfer speed and image quality were two areas that heavily influenced the app's UX. I was always searching for ways to improve both of those areas. Image quality is generally determined by resolution. Here are two identical manga pages. The one on the left has been resized to 1200 by 800, and the one on the right has been resized to 600 by 400. Let's try zooming in on the text area. On the right one, the text is jagged and hard to read. Because manga has a lot of text, it's very important to ensure that the text is easy to read. On the other hand, we have to consider the file size. One is 100 kilobyte, while the other is 40 kilobyte. About 2 or 3x difference between the two file sizes. So mobile carriers in Japan often limit the network speed to 64 kbps. With this condition, it is considerable difference that can affect the UX. This is the trade-off. What if it was possible to maintain high-resolution image while reducing the file size? This problem can be solved using super resolution, which is our main topics for today. Super resolution is a type of technology that converts low-resolution image into high-resolution image. Research on super resolution began a long time ago, but thanks to machine learning and deep learning, the field has seen incredible advancement in recent years. In addition, last year, Apple introduced CoreML framework in iOS 11. With CoreML, machine learning and deep learning have become very easy to execute on iOS device. I consider the possibility of combining super resolution technology with CoreML. Could we conduct super resolution using CoreML on iOS device? If that's possible, then we should also be able to keep the image file size small while displaying a high resolution image. This would have the potential to dramatically improve the app's UX, so I looked into this technology further. Let's go to the demo. This is a manga app created for today's demo. As you see, image quality is very poor because this is a low-resolution image and hard to read and very jagged. So turn on super resolution function. Can you see the difference? Another part. This jagged line become very smooth. So I have another manga. So this manga is written by my brother. So my model is trained by using this manga's data. So my model is don't know this manga. Try. Strange. Well, works fine. How is the photo? Oh, sorry. Well, works. Oh, okay. Yes, this model is optimized for manga. Okay, let's go. Go back to the slide. This brings up the question: what kind of mechanisms are needed to execute super resolution? Let's take a look at detail. This is a research paper called Image Super Resolution Using Convolutional Network, published in 2015. This paper is about the method called super resolution using convolutional neural network, in short, FSRCNN. FSRCNN is a super resolution method using convolutional neural network. Oh, sorry. So what is CNN? In order to understand what a CNN is, it is necessary to explain kernel and convolution. Kernel are float values on a two-dimensional array, like a filter. For example, this is a kernel with pixel size of 9 by 9. The pixel with large value are displayed as white and low value as black. You can see it kind of looks like a diagonal line stretching down from the top right to the bottom left. Meanwhile, convolution is a computational process. If you have the input image like this, we take the sum of the product of pixel value and kernel value by gradually moving kernel across the entire input image. By doing so, you get an output image like this. You can see that only the diagonal line section is emphasized and displayed as white. All other parts are black. This shows that the feature of the diagonal line section of input image are extracted by convolution process. So that's a little about kernel and convolution. As you may know, neural network is a type of computational graph. Each node has an input and output, and they are mutually connected to each layer. Moreover, convolutional neural network is a type of neural network where each node retains a kernel. If you put an image into the network, convolution process is executed many times. Through repeated convolution, you can extract a lot of features from the input image. The extracted feature can be used for incredibly advanced image processing. SRCNN is a super resolution method using CNN. With SRCNN, the final layer of the CNN is aggregated in the single node and is designed to produce a single high-resolution image as its final output. For example, first you input a low-resolution image into the model. Then the model applies each kernel of layer 1 to input image, and the output, this image. This output will be used as the input for each node of layer 2, and output these images. Finally, all the output of the final layer are put together to form a single image output. This output is an image that has gone through super resolution processing. The role of each layer as follows. Layer 1's role is to extract feature. Layer 2's role is to restore the resolution. Layer 3's role is to combine them to obtain a single image. In order for the model to output higher quality image, it is necessary to train and optimize each weight of the kernel. Next, I will explain how to train the model. A lot of training data is required in order to acquire higher performance machine learning model. For example, a lot of data with label is required for the image recognition or classification task. In most cases, you need to add the label manually, and this can be a very tedious task. This is one of the hurdles of machine learning. On the other hand, it's simple to prepare training data for super resolution. As long as you have the original high-resolution image, you can create a low-resolution version from that simple and automatically. First, obtain patch images by breaking up high-resolution image into patch images. Second, resize patch images to 50% using bicubic interpolation. Bicubic interpolation is a method for image resampling. That's all. It's very easy. These pair make up the training data to be used in the actual FSRCNN model training. In the FSRCNN model training, first, low-resolution patch image input into the model and execute super-resolution processing and output image. A loss function is used to compare the margin of error in pixel between the output image and training data. This margin of error is referred to as loss. This loss is transmitted to each kernel of a model, and the weight of the kernel is finely tuned. By repeating this over and over again, the kernel learns how to take the shape of the meaningful filter. Ultimately, they can be trained to a level where the FSRCNN can output an image relatively close to that of training data. For example, this is the weight of the kernel before training. The weight of the kernel are decided randomly, so it just looks like noise. After training, for a while, the kernel weight changes to start to look like this. It no longer look like noise. For example, this is similar to the shape of the Gaussian filter for image processing. And this shape is like a Laplacian filter. And this image is like an edge detector's shape for image processing. So through training, the FSRCNN model is capable of discovering these filters on its own. This is very interesting. Now that we know about FSRCNN, let's take a look at how to implement. First, I create the machine learning model. The detailed parameters were implemented as described in the original paper. The total number of parameters is approximately about 85,000. In other words, we use machine learning to obtain the optimal parameter value. This is the training code. As you can see, the code is written by using Python and Keras. Keras is a deep learning framework. The framework will perform all of the complex processing. Once the training is complete, all information, including the network structure of the model and the kernel weight, will be stored in the file model.h5. Once training is complete, we need to convert Keras model into ML model format so that it can be embedded into iOS app. Apple has a Python library for conversion called CoreML tools. So by writing just a few lines of Python code, such as this, we can obtain the ML model file. You will notice here that the file size of the model we created is quite small at only 440 kilobytes. Apple has released a large number of pre-trained ML models, and if you compare the file size with my model, you will see just how small our file is. Since the model size is small, there is no worry about enlarging the binary size of your app. All that's left to do is to add the model to the iOS project. Xcode will automatically generate the class in order to access the model. The rest is simple Swift programming. You just call predict method. It will return your image object converted to high resolution. That's all that is needed for implementation of super resolution on iOS app. I think you now have a good understanding of how the previous demo worked, but we are not done yet. Since these papers publication, research on super resolution of even higher precision has been continually presented on. One interesting aspect of machine learning is that it is a rapidly evolving field. Let's see how we can further improve the model's performance. I would like to talk about paper presented in 2016. It is a follow-up paper to FSRCNN, written by the author of the original FSRCNN himself. In this paper, he proposed an expansion to FSRCNN, a model called FSRCNN. The feature of the model is, as the name includes fast, the processing is fast. Let's see how fast it is actually in the demo. Let's go to the demo. This is the, so first I try to original FSRCNN. It takes around 1.5 seconds. So next, try to FSRCNN. Sorry. FS about 1.1 second. 1.1 second, about 45% faster. So go back to the slide. Although we will skip the detailed explanation, FSRCNN is a model which just changes the structure of the network slightly from SRCNN. It is more deeper and smaller. This is an output of FSRCNN. Let's look at the number of the parameters of the entire network. In SRCNN, the number of parameters was about 85,000. In FSRCNN, it's about 12,000. This is about a seventh of the previous model. This huge decrease is the reason for the faster processing speed. I measured the performance of each method using iPhone 10 device. FSRCNN clearly shows the best performance. Prediction time and training time are very fast, and the model size is very small. On the last row, I show the PSNR, peak signal to noise ratio. It shows the image quality. Both of SRCNN and FSRCNN show high value. As you see, slight change in the network structure dramatically improves the performance of the model. Even now, super resolution is an active research field. The following paper especially looks really great. We need to catch up with this for further improvement. Of course, super resolution is useful for any type of images, not only manga. And everyone here today can easily make use of it too. Give it a try. Open source. The name of the repository is Super Resolution Kit. It supports Cocoa pods, so all you need to do is use pod install to set it up. By simply calling a set SR image method on your image view, you can display the super resolution version of the image. It's very easy to do. My super resolution kit is made up of the following code. First, it offers UI image view extension and SR converter class for conversion processing. And it includes pre-trained FSRCNN and SRCNN model. If you just use it for testing, it is not necessary to train the model. And for anyone who wants to train model using their own trained data, it also includes Python scripts. Super resolution kit works well in many cases, but it has few limitations. First, this training model is not trained enough. It needs more training for the production. Second, the quality of the super resolution is dependent on the type of image. For example, if you use our model to train from manga images, you maybe not get good result with image other than manga. Keep in mind this limitation. Please try it yourself. So up to this point, I will talk about super resolution and CoreML. But lastly, I want to shift the perspective slightly to talk about how ML technology can be applied to mobile app development. CoreML has made it possible to execute various ML-based processing on the device, but I think it is important to always consider whether it's really necessary to do this on the device. Even if you have cool ideas with involving CoreML, sometimes you may reach the conclusion, why not just run all this on the server side? Therefore, we need to ask ourselves why we need to run ML on the device and clearly define the purpose of doing so. In my case, it made sense because we had a clear goal to maintain the image quality but reducing the file size. I will go through some other cases where you might want to consider running ML on the device because we need to, for example, quick response or offline support, or reducing server and network cost. Maybe this super resolution case is from this. Lastly, from security perspective, there are various ways to integrate machine learning model into app. It's important to choose the right method for the goal you are trying to achieve. In many cases, you can use Vision Framework or CreateML or Turi Create. It's very easy. For other cases, you have to run the theories by reading research papers or books, create a model with Python and CoreML, and then train it yourself. Please choose the best way. Finally, should Swift engineer learn Python if they want to learn machine learning? For now, yes. Other than Python, there is fundamental machine learning related libraries such as NumPy, Keras, and TensorFlow. However, in the future, we might not need to write Python. One reason is that if you use the dynamic member lookup feature in Swift 4.2, you can directly call Python APIs. This is kind of like how you can call Object-C API with Swift. For example, this is my training code using Python. And this is code using Swift and dynamic member lookup. It's very similar to the Python version. Maybe almost Swift programmers can understand this code. Additionally, it's also worth noting that Chris Ratner, the founder of Swift, is developing a Swift for TensorFlow. This project aims to increase ML programming performance and expressiveness and ease of development by rewriting Swift compiler. In conclusion, today I talk about the detail of super resolution. I also talk about how to implement super resolution using Python and CoreML. Additionally, I will introduce you to Super Resolution Kit, an OSS project that includes everything I talk about today. I'm looking forward to seeing your contribution. I hope that after listening to this presentation, you are more interested in super resolution or machine learning. If you have any question, please come to QA booth. Thank you for your attention.